Welcome to the next lecture on the course Descriptive Statistics with R software. You may recall that in the earlier lecture we had considered the aspect of measuring the variation by using the absolute deviation and absolute mean deviation. And if you recall, we had developed that tool on the concept of deviations of the observations around any arbitrary point or around some central tendency value like as mean or say median, like this. We also discussed that whenever we want to develop these types of tools, we had to convert the deviations only into a positive value. That means we needed to convert or we needed to consider only the magnitude of the deviations, and for that we have two options. We try to consider the absolute value of the deviation, or second option is that we can consider the square values of those deviations. So, now in this lecture we are going to discuss the second aspect, that how to build up a measure of variation by considering the magnitude of the deviations by squaring them. So, in this lecture we are going to discuss the concept of mean squared error, variance and standard deviation, and we will try to see that how to implement it on a R software. So, before we start, let us try to fix our notations once again, although I had done it in the earlier lecture, but here I will be just doing it quickly. So, we will be considering here two types of variable, one discrete variable on which we will have ungrouped data, and in this case the variable is going to be denoted by capital letter X, and on this variable we are going to obtain the n observations, and these observations are denoted here like small x1, small x2, small xn. Similarly, when we are trying to consider a continuous variable here and we have grouped data on that variable, this means we have a variable, continuous variable x, on which we have obtained the observations, and those observations have been tabulated in k classes or say k class intervals, and the entire tabulation has been presented in the form of a frequency table. For example, here you can see the frequency table in which all the observations have been converted into the groups, and these groups or the class intervals, they are denoted by here E1 to E2, E2 to E3 and so on. So, we have here k class intervals or say k groups, and after this whatever is the midpoint of this interval, that is going to be denoted by here x1. So, x1 is going to denote the midpoint of the first class interval, x2 is going to denote the midpoint of the second class interval and so on, and all these x1, x2, xk here now in the case of group data, they are going to denote the midpoint and not the value of the observation as it happens in the case of ungrouped data. And the frequency of these intervals is denoted by here f1, f2, fk. So, f1 is going to denote the frequency of the first class interval, f2 is going to denote the frequency of the second class interval and so on, and the sum of all these frequency is denoted by here n. So, that is going to be our basic notations for grouped and ungrouped data. So, as soon as I say that we are going to define the measures on grouped data, I will be using these notations, and as soon as I say that I am going to develop the tool for the ungrouped data, then I will be using the earlier symbols and notations. Right. Now, I come on the aspect of developing a tool called as mean squared error, and I will be following the lecture almost on the same line as I did in the earlier lecture. You may recall that first I defined the absolute deviations, and these deviations were defined around any arbitrary value a, and then I developed the measure, and then I replace A by some measure of central tendency, and we defined the absolute mean deviation by replacing A by the median, because median was the value around which the absolute deviations were minimum. Now, similarly on the same lines, now instead of absolute deviation, I will be considering the squares of the deviations, right. So, if you remember that in the case of absolute deviation, I have used the quantity absolute value of xi minus a. Now, I will try to consider the squared values of xi minus a, and I will write down here the squares of these deviations as xi minus a whole square. So, these deviations are the squared deviation around any arbitrary point A. Now, I will try to obtain this quantity for each and every observation, say x1 minus a whole square, x2 minus a whole square, and up to here xn minus a whole square. And then I will try to take the arithmetic mean of all these values. And once I try to do it, then in the case of ungrouped data, discrete variable, this quantity is denoted by here like this. You can see here this is the same quantity what I have given here. This quantity is denoted here as a s square a, which is called as mean squared error with respect to a. And similarly, whenever we have continuous variable or grouped data, then in that case the mean squared error with respect to any arbitrary value a is defined here like this. So, you can see here that now this summation is going over the number of classes, and here this is small n is here the sum of all the frequencies, and this quantity is a sort of weighted mean where the weights have been given by the frequency fi. So, this is how we try to define the mean squared error in case of group data and ungrouped data with respect to any arbitrary value a, right. Now, one can choose any value of a. So, this can be shown mathematically that the mean squared error is going to assume the minimum value when a chooses the value arithmetic mean, or in simple words I can say mean squared error takes the minimum value when the deviations are measured around the arithmetic mean. So, now what I will do? I will try to replace capital A by x bar, which is the sample mean or the mean of the observations. And when I try to do it, then what happens? That I simply try to replace A by here x bar. X bar here is 1 over n summation I goes from 1 to n xi, that is the arithmetic mean. And then I try to define here the deviations x1 minus x bar whole square, x2 minus x bar whole square, and up to here xn minus x bar whole square. And then I try to find out the average of these things, simply arithmetic mean, and this quantity is denoted here in the case of ungrouped data or the discrete variable, that these values are the values which are given here in case of a ungrouped data or a data on the discrete variable. So, you can see here this is the same thing, and this quantity which is essentially here s square x bar, which is in general we denote by here s square, this is called the variance. And in case if you try to simplify this expression, so you can write down here this same thing here 1 upon n I goes from 1 to here n x I square plus x bar square minus twice of xi into x bar. So, this comes out to be 1 over n summation n xi square plus this will become here n upon n x bar square minus twice of x bar summation xi I goes from 1 to n upon n. Now, this can be further simplified to I goes from 1 to n summation xi square divided by n plus x bar square minus this quantity is simply the x bar. So, this becomes here twice of x bar square. So, this quantity becomes here 1 upon n summation I goes from 1 to n xi square minus x bar square. So, the alternative expression for the variance is here given by this thing, which is the same thing. So, actually you can use any of this expression to compute the value of variance in case of ungrouped data. And similarly, when we have group data on a continuous variable, then in this case the variance is defined like this. So, this is 1 upon n summation I goes from 1 to k, where k is the number of classes, and then multiplied by fi into xi minus x bar whole square like this, and where x bar is defined like this, and this is small n is defined as the sum of total frequencies. Similarly, if you want to simplify this expression as we did in the earlier case, you can see here this will also come out to be I goes from 1 to k fi xi square plus x bar square minus twice of xi x bar, and if you try to see here, this is 1 upon n summation I goes from 1 to k fi xi square plus x bar square summation fi I goes from 1 to k upon n minus twice of x bar summation I goes from 1 to k fi xi upon here n. So, this quantity here becomes here same as x bar. So, I can write down here 1 upon n I goes from 1 to k fi xi square plus x bar square. Why? Because the numerator summation fi becomes here n upon n minus here twice of here x bar into x bar. So, this quantity comes here 1 upon n summation I goes from 1 to k fi xi square minus x bar whole square. This is the same quantity given over here. So, any of this expression can be used to compute the variance in case of grouped data. Now, after giving the definition of variance, I would like to address here one more aspect. You have seen that in the definition of variance, I am trying to take the average of n values. So, this is defined as 1 upon n summation I goes from 1 to n xi minus x bar whole square. In statistics, there is another expression of variance that is quite popular, and this expression is given by this. In case of ungrouped or discrete data, this is given by here this quantity. You can see here that this expression is like the earlier one. The only difference here is that instead of here n, I have here 1 upon n minus 1, and earlier we had only here n. So, this is what you have to keep in mind. And similarly, in case of continuous data or a group data, the divisor that was earlier n, now this becomes here 1 over n minus 1. Now, an obvious question comes that why I am using this expression. Actually, the properties of this expression when we have divisor n or when we have divisor n minus 1, they are different. If you have the idea of an unbiased estimator in the context of statistical inference, then when I say or when I use the divisor n minus 1, then this form of the variance is an unbiased estimator of the population variance. Whereas when I am using the divisor n, then 1 upon n summation xi minus x bar whole square is not an unbiased estimator of the population variance. So that is why many times the software uses this definition. For example, in the R software, this definition is used where the divisor is n minus 1. So that is the reason I would like to inform you here that whenever you are using any software, please try to look into the manuals of the software and see what they are trying to do. Well, in case if the data is very large, then the value of the variances may not differ much. But in case if the data is small, can the values of the variances computed by using the divisor n or say n minus 1, they may have difference. So you should know what you are obtaining. It should not happen that you are assuming that the divisor is n and your divisor is actually inside the software is n minus 1. Okay. So just be careful. Now after the variance, I come to another concept that is called standard deviation. You have used possibly two types of terminologies. One is standard deviation and second is standard error. Possibly in general people do not differentiate between these two names, but here I would try to explain you that what is the difference between the two. But to start with, I will try to use the common terminology and I will use here the standard deviation. Right. So when I say that S square is going to denote my variance, then it is actually the sample variance. Sample variance means that the variance calculated on the basis of given set of data or given set of or given sample of data. Right. So essentially we are trying to compute the sample variance, but we always call it without loss of generality as variance. When I try to take the positive square root of S square, then this is called as sample standard deviation. So once again you can see here I am writing here the sample word inside the bracket just to indicate you that the common language is simply the standard deviation. But here actually we are trying to compute the standard deviation on the basis of given sample of data. Right. Once I am saying that the sample variance or the standard deviation has been computed on the basis of given sample of data, what does this mean? If you try to see in statistics what happens, that you are usually trying to collect a sample of data, and on the basis of sample of data your objective is to compute the population counterpart. You may recall that in the beginning of the lectures we have discussed the concept of population and sample. So suppose I would like to compute the total number of people who are eating say more rice in the country like India, which is a very huge country, a very big country. Now if I want to find out the arithmetic mean, the average number of people who are eating more rice than wheat, then what I have to do? I have to compute the number of such persons all over the country, which is very difficult to compute unless and until you execute a census. So we try to take a sample of data. That means I will try to choose a small number of observation, and based on that I will try to find out the mean, and that will be called as sample mean. Similarly, if I want to find out the variance of the data that I have collected inside the sample, then that will be called as sample variance. But there will always be a counterpart like as population mean or population variance. Population mean means the arithmetic mean of all the population. Simply the population variance means the variance of all the units inside the population. So what happened that when we are trying to compute the positive square root of the population variance, then this is called as standard deviation. But the problem is this: we do not have the entire population in our hand. So, we always work on the basis of a sample of data, and that is why in a common language people do not differentiate much between the two definitions, standard error and standard deviation. But once you are trying to do a course on statistics, as a student you must know it. So, and that is my idea to explain this concept here in the next couple of slides. Okay. So, now I will try to denote sigma square as the population variance, and the positive square root of sigma square, that will be called as standard deviation, or this is actually the population standard deviation. But as I said, this using sigma to denote the standard deviation and using sigma square to denote the population variance is a more popular notation among the practitioners. Now, next question comes: what is the advantage of having a standard deviation or say standard error in place of variance? Now, if you try to see, suppose I am trying to collect the data on the height of some children, say in meters. So, the arithmetic mean will be in meters, but the variance will be in meter square. So, if I try to see that say that there are two data set whose variances are say 16 and 36, then it is more convenient to compare the two values if they are in the same units as of the original data set. So, what we try to do? We try to find out the positive square root of 16 and 36, which are 4 and 6 respectively. So, now once I say that I have got a data set in which I have measured the heights of the children in meter, and then they have got the arithmetic mean of say 1.2 meter and standard deviation of say 0.5 meter, then it is more easy to understand. And similarly, if I say that I have got two data sets in which the standard deviations are 4 and 6, then it is more easy to understand that the standard deviation of the second data set is higher than the standard deviation of the first data set. That is the only reason actually. So, this standard deviation or standard error has an advantage that it has the same unit as of the original data. So, that is easy to compare. For example, if I have a variable in which I have taken the observations denoted as say small x, then if this small x have been obtained in the unit meter, then variance s square will be in meter square, which is not so convenient to interpret also. On the other hand, if I have obtained the observation x in meter, then the standard deviation s will also be in meter, and which is more convenient to use, more convenient to interpret. That is the reason that why people prefer to use the tool of standard deviation or standard error. Now, the question comes, what does this variance or standard deviation actually measures? The variance or say equivalently standard deviations measure how much the observations vary or how the data is concentrated around the arithmetic mean. For example, if I try to take here a data set, and suppose this data set is like this, and suppose there is another data set which is here like this. So, you can see here in both the cases the mean is somewhere here, but these deviations in the case of red dots and in the case of green dots, they are different, and the deviations in the case of red dots, they are larger. So, in this case, if I try to find out the value of the variance, see here variance 1 and here variance 2, then if I try to compute the value of variance variance 1 and variance 2 on the basis of given set of data, then we will find that variance 1 is smaller than variance 2. So, whenever I have a value of variance, say variance equal to 4 and variance equal to here 10, then this obviously indicates that the data in the variance 1 is more concentrated around the mean value, and the data with variance 10, suppose I am denoting in the red dot, that is more scattered around the mean value, which is here like this. So, this is how we try to take the interpretation of the value of the variance. So, obviously, when we want to make a decision on the basis of a given value of variance, then the lower value of variance or equivalently the standard error, standard deviation indicates that the data is highly concentrated or less scattered around the arithmetic mean. Whereas, the higher value of variance or the higher value of equivalently standard deviation or standard error indicates that the data is less concentrated or highly scattered around the mean. So, this is the interpretation, and obviously on the other hand, if I have a data set which has got the higher value of variance or the standard error or standard deviation, then I can say simply that the data set has got more variability. In statistics, usually we always prefer to have a data set which has got the lower value of variance or lower value of standard deviation or standard error. So, in case if I have got two data sets and suppose we compute the variances, and suppose these variances are coming out to VAR1 and VAR2, then if VAR1 is greater than VAR2, then we say that the data in the variance 1 is having more variability or less concentration around the mean than the data in the data set used for computing the variance 2. Now, there is a very simple rule. We would always like to have a data which has got lower variance, and if you remember in the initial slides I had discussed that one of the basic objective in a statistical tool is that we would always like to have a data in which the variability is less. Okay. Now, in case if you try to compare the variance and absolute mean deviation, then you know that when there are some outliers or some extreme observation inside the sample, then the median is less affected than the arithmetic mean. And in this case, means if the data has very high variability or the data has extreme observation or say outliers, then in this case using the absolute mean deviation is a better option and it is preferred over the variance or standard deviation. Whereas variance has its own advantages. For example, if you are working with the statistical tool, then the variance has some nice statistical properties. So, from the statistics point of view, from the algebra point of view, from the statistical analysis point of view, it is more easy to operate on the variance mathematically, algebraically than on the absolute function like as absolute median deviation, or we call it say here absolute mean deviation. Next, we try to understand what is the difference between standard deviation and standard error. To understand this thing, we have a concept which is called as a statistic. You see, the spelling of the subject statistics is STATISTICS, but we are not using here the last S, and this is called only as a statistic. A statistics is a function of random variables. So, if you have random variables x1, x2, xn, then any function of x1, x2, xn is called as a statistic. For example, if I say you have random variables x1, x2, xn and you try to find out the arithmetic mean, like as here capital X bar 1 upon n summation I goes from 1 to n xi, then this is this x bar is itself a random variable. So, this is called as statistic. Now, the concept is very simple. Whenever you are trying to find out the standard deviation of a statistic, then the outcome is again going to be a function of only the random variables. And this standard deviation is called as standard error. So, whenever we try to find out the standard deviation of a statistic, it is called as standard error. What does this mean actually? Actually, ideally what happens that standard deviation is a function of some unknown parameters. For example, if you try to understand, suppose mu is representing the population mean, right, the mean of all the units inside the population, which is very, very large. And practically it is very difficult to find out the mean of entire population. So, usually it is unknown. Then ideally the standard deviation is defined as the positive square root of the variance of all the values in x, which is denoted here as a square root of sigma square, which is equal to here sigma, and that is equal to square root of 1 upon n summation xi minus mu whole square. So, mu here is actually the population mean of all the values xi's. But since this mu is not known, this is unknown, so you cannot compute it, this value cannot be computed. Why? Because how you will get the value of mu? So, then in that case the sigma square cannot be found. So, one option is this, that we can replace the value of mu by its sample counterpart. So, when I say mu is here what? This is the population mean. So, this is equal to 1 upon the total number of units in the population, which is population size. I goes from 1 to here population size and say here x size. So, I try to replace it by the sample value. So, this is for population, and now for sample I try to replace by 1 upon say here n number of observation. I goes from 1 to n, say here xi, and I denoted the arithmetic mean to be here x bar. So, now mu is unknown to us, but sample mean x bar is known to us. So, what I can do, I can replace mu by the sample mean x bar 1 upon n summation I goes from 1 to n xi, and then in that case the standard error, which is the positive square root of the variance, becomes like this, square root of 1 upon n summation I goes from 1 to n xi minus x bar whole square, and this quantity is called as standard error. So, standard error, always remember, standard error will always be a function of observed values. So, in simple language I can say that the standard error will always refer to a standard deviation which can always be computed on the basis of given sample of data. You have got the data, you are asked to compute the standard deviation, you can compute it, and in that case this will be called as standard error. And in that case, if you try to see here more specifically, the population variance was defined here like this, and now this becomes s square is equal to 1 upon n summation I goes from 1 to n xi minus x bar for the case when we have ungrouped data, and 1 upon n summation fi xi minus x bar whole square in case of we have group data. So, this is basically the definition of sample variance, and in common language we usually do not call again and again it to be sample, but we simply call it that find out the variance of the set of given data. Now, after this I will come to the aspect that how are we going to compute the variance or standard deviation on the R software. Right. So, I will take the first case here, the case of ungrouped data. So, in this case the data vector is going to be denoted by say here a small x, and the R command for computing the variance is here VAR, and inside the argument you have to give the data vector. But remember one thing, this command VAR and inside the data vector x gives the variance with the divisor n minus 1, that is this value. So, in case if you want to obtain 1 upon n, I goes from 1 to n xi minus x bar whole square quantity, then what I can do, I can multiply and divide it by the quantity n minus 1. So, now this I can write down here n minus 1 upon here n into 1 over n minus 1 summation I goes from 1 to n xi minus x bar whole square. So, in case if you are very particular in getting the divisor n in the variance, then in that case I would like to suggest that you try to use this command, try to multiply the variance of x by the factor n minus 1 upon n. How? For example, you can see here, now I am writing in red color, this quantity will give you variance of x and this quantity will be the factor by which if you try to multiply the variance you will get the variance with divisor n, and where n is the length of the x vector, that is the number of observation present in the data set. Now, we are going to consider the case when we have the group data. Now, in the case of group data, you know that there is no built-in command in the base package of R. So, I need to compute the mean value of the given data set separately along with the midpoints from the frequency table and the frequencies from the frequency table. So, in this case we are going to compute the mean as say x mean separately, and in this case if you try to see your expression for variance was I goes from 1 to k fi xi minus x bar whole square. So, now this x bar becomes x mean, and then this quantity here I am trying to write down here x minus x mean whole square, and then it has to be multiplied by the frequency vector here f, and then this has to be sum, means all the elements in this vector will be sum divided by the n, which is the sum of all the elements in the frequency vector f. So, this is how this expression has been obtained to find out the variance in case of group data. And in case if you have some missing data, then in the case of ungrouped data, if the data vector x has some missing values as say na, then we are going to denote this data vector as say here x na, and in that case the command remain the same, but I have to give here the option na dot rm is equal to true, right. And similarly, if you want to compute the standard deviation, that is very simple, simply try to find out the square root of the variance that you have obtained earlier. So, if I try to find out the square root, which is a function sqrt of the variance of x that we had earlier obtained, then this is going to give you the standard deviation or the standard error, right. But in this case you notice that the divisor is going to be n minus 1. In case if you want the divisor to be n, then in that case simply try to take the square root of the earlier expression that we had obtained, right. So, finding out the standard deviation is simply equivalent to finding out the square root of the variance and considering its positive value. And similarly, in case of grouped data also, whatever the expression you have obtained for the computing the variance, just try to take the square root of the variance, and this is how you can compute the standard deviation in the case of group data. Now, I try to take the same example or the same data set that I considered earlier, where we have the data of 20 participants who participated in a race and their time taken to complete the race was recorded, and this data is stored here in this data vector. Now, I try to find out the variance of this data vector, and I use the command var, and inside the argument the name of the data vector, that is time, and I get here this value 283.3684. And here you can see the divisor here is n minus 1, that you always have to keep in mind, and I will show you that how to find out the variance with divisor n in the next slide. Similarly, if you want to find out the standard deviation, then you simply have to take the square root of the variance. So, whatever variance I have obtained here, I am trying to operate the function SQRT. SQRT is a function to find out the square root, and I get here the value 16.83355. Similarly, if you want to have the variance or standard deviation with the divisor n, then in this case we have learned that we need to multiply the variance x with the factor n minus 1 upon n, where n is the length of the data vector. So, I simply try to multiply this n minus 1 upon n in the given variance that we have obtained earlier, and I will get here the value of variance with divisor n. And similarly, if I try to take the square root of this value, then I will get the standard deviation, which is based on the divisor n. So, you can see that it is not difficult to operate or get the variance or standard deviation on the given set of data, and here is the screenshot which I will try to show you. Now, next we try to find out the variance in the case of group data. So, we consider the same example and we try to convert it into a group data. We try to find out the frequency table, and from there we will try to find out the frequency vector, vector of midpoints and the arithmetic mean. We already had discussed this aspect, that how to find out the frequency vector, vector of midpoints, and how to create the frequency table. So, I will not discuss here, but I will very briefly give you the background so that you can look into the earlier lectures how to get it done. So, you see the given data has been classified in 6 class intervals, and these are the midpoints and these are the absolute frequencies that we already have obtained, and now we need to find out the frequency vector and mean from the given data. So, we had used the command breaks and then cut command, and whatever is the outcome of this cut command, we had created a frequency table using the table command, and after that we had operated the as numeric on the data obtained from the earlier command, which has given us the frequency like this one. And we had created the vector of the midpoint from the given output from here like this, right. So, now we have obtained the x and f vector. So, now I can say here that in case if you want to find out here, we already have obtained x, we have already obtained f. Now, I need to find out the mean of x. You can see here that in this case mean of s is going to be defined by summation f I x I goes from 1 to k, right. So, you can see here I am trying to define here at x mean, and this is sum of f I x I divided by n, which is sum of f, and if I try to do it here, I get here the value of here x mean to be 56. Now, I try to use the command or syntax that we had defined earlier using with the given set of data here, and this gives me the value here 269, and if I try to find out the standard deviation of this quantity, this is here, this will give me the value of the standard deviation in this case. And this is the screenshot whatever we have obtained here. And similarly, at the same time I would try to show you that if you have some missing data, so then how to handle the situation, how to find out the variance and standard deviation. So, in the earlier example, I am trying to take the first 2 values to be missing, and I am denoting the data inside a new vector time.na, where 2 values are missing. And if I want to find out the variance, it is simply the variance of time.na with the command na.rm is equal to true, and this will give me the value of the variance as 250.2647. This will have the divisor n minus 1, and in case if you want to convert it into the divisor n, then you know how to get it done. And if I try to take the square root of this value, this will give me the standard deviation when we have the missing values are present in the data, right. And this is here the screenshot you can see here. Now, I will try to come on the R console and I will try to show you that how you are going to obtain these values. Okay, so, I try to first take it here the time. So, you can see here I am copying the data on time. I will put it in the R console and I try to find out here the variance of here time, and you see I get here this value. If I want to find out the standard deviation, I simply have to find out its square root, and you can see here this is the value. And similarly, these values have been obtained with the divisor say n minus 1. If you want to have the divisor n in the variance, then you just use the same command and you get here the outcome. And if you want to find out here the standard deviation by the divisor n, then you simply have to find out this square root of the earlier expression, and this gives you the value 16.40732, and this is here the same screenshot which I have shown you here, right. And similarly, if you want to find it out in the case of here this grouped data, then first I need to create here the data vector x and f, which I already have done. So, you can see here I can clear the slides. X is here, my midpoints, f is here like this, and if I try to find out the mean in case of group data, this is coming out to be 56. And now, if I try to find out the variance in this case, this is going to be by the same command that we discussed here like this. This is 269, and if you want to find out the standard deviation, you simply have to find out its square root. This is coming out to be like this. And similarly, if you want to see that how the things are happening in case of missing values in the data, so I simply need to use this command here, and you can see here that this data time dot na I already have copied here, and if you try to find out the variance when this na dot rm is equal to true, this gives me this value. And if you want to find out the standard deviation in this case, then this is simply the square root of this value that we have just obtained, and it is coming out to be here like this. And if you try to see here, this is here the same screenshot that I have shown you here. So, now I would like to stop in this lecture, and I would request you that we already have discussed the concept of variance, which is one of the very popular tool to find out the variability in the data. Please try to understand it, please try to grasp it, and try to see that how this measure has been developed, and please try to take some data sets and try to compute the variance with divisor n and with divisor n minus 1. Try to compute the mean squared errors around any arbitrary value, and get comfortable in computing the variance or standard deviation or standard error using the R software. So, you practice, and we will see you in the next lecture. Till then, goodbye.